Can you hear me?
Yes, we can.
Yes.
That's good. Okay, so today we're going to start the chapter 3. It's about the scheduling. But before we do this, let me summarize the topics we just talked about last time. So in chapter 2, we covered the materials of multiple processes. Okay, so in a typical, computer system, multiple processes are going to be supported. So this can be achieved by two different ways. One is using the multiprocessor. Okay, in that case, we use multiple processors. So like the system with multi-core system, so you have 2 cores, 4 cores, or even 8 cores. So in that case, if you have a multiple processes, then you can allocate different processes to different processor. Okay, so just hear me clearly. So you have a multiple processes, right, which is actually the execution of program. And then if you have a multiple processors, that means multiple CPU or multiple microprocessors, whatever you call it. If you have a multiple processors, then you can allocate different processors to different processors. Okay, so this way we can achieve the multi-programming. This is, of course, this is the best way, because you have multiple physical processors to process the different processes. Okay. Now the other approach is we assume that there's only one processor, and we still want to support multiple processes. Okay. Now, how can we do this? So we use a technique called, what is this technique?
You could use multi-programming, and then like time sharing is kind of like a derivative of multi-programming, where you have like multiple processors, like using this processes using the same CPU.
You're using the multi-programming, and in particular using the time sharing. Yes, that's correct. So in that case, so at each particular time, the CPU, there's only one CPU, so the CPU can actually execute only one process at the particular time. So if you take a time, a snapshot of a particular time, the CPU is only processing one process. Okay, so in that case, all the data, all the information, all the variables going to be stored in the CPU register. So the CPU can actually execute this particular process. However, if we use the multi-programming or time sharing, that means the CPU going to switch back and forth among these processes. So the PCB is basically used to store the current state of each process. So every time the CPU decide to switch from this process to the other process, then CPU need to save every information in the CPU registers and from instruction registers and from all the registers in the CPUs, and store the data in the registers into the PCB, because you have to store the data. Otherwise, when it's time for the processor to actually execute this process again, then you have to make sure that what was the last state. Okay, so you have to actually reload every data stored in the PCB back to the registers. So that's basically why we use a CPU to record the state of the process. Okay, so if we have 3 processes, P1, P2, P3, then you need to create 3 PCBs, PCB1, PCB2, PCB3. And we also mentioned that, in most actual modern systems also support multi-threading. So, which means that some of the processes, like a P4 in this case, they have multiple threads. So multiple threads basically, multi-threading basically means that each of the threads in the process basically executing the same program, but they have a different thread of control. So each thread is kind of independently executing its own code, even though they are executing the same code. So in this case, you have like a 3 thread, T1, P2, T3. Now to correctly record the process, you also need a PCB, right? PCB4. However, since each thread has its own thread of control, so some of the data should be, dedicated to a particular thread. So that's why each thread has its own thread data. Sometimes we call it TCB, thread control block, thread control block, thread control block 1, 2, 3, corresponding to each thread. And these thread control data basically associate with this process control block, because thread is actually associated with a process. And we also talked that the thread has 2 different types. One is called a user level thread. The other one is called a kernel level thread. And the difference between these 2 is user level threads, the thread control block, the data structure that dedicated to each of the thread are actually located in the user space. So the computer operating system kernel may not, know the process 4 has multiple threads. Okay, they may not be aware of the multiple threads in process 4 because it's in the user level. And there's another one is kernel threads. Kernel threads basically means that a process 4 has multiple threads, but each of the threads is also information is stored in the kernel space, so that the operating system is aware of the multiple threads. Now these 2 are very different, and there's an advantage and disadvantage for each approach. For user threads, it's pretty easy to create a multiple threading because it's, the user program can actually do this. Okay, it's just actually at the user level, so you can actually allocate the CPU time, wherever actually CPU allocate the time to process 4, and then it's the user can manipulate that CPU time, to each of the threads. Now for the kernel thread, so then the CPU actually scheduler gonna be able to allocate each of the threads. So the operating system actually aware of these multiple threads. So that's good, because then the CPU can, the operating system scheduler can actually allocate the CPU time for each individual thread, even though the thread is part of the process 4. So however, the disadvantage is that because it's in a kernel thread, it's very, very difficult to create and very, very difficult to manipulate. Okay, so that's the trade-off. So Now, actually, back to the next chapter, chapter 3. So because we have a multiple threads, multiple processes and multiple threads, then we need to manage all these processes. We need to manage the executions of these different processes. So the operating system has to do this. So next, in this chapter, chapter 3, we're going to talk about the scheduling. Okay. How the operating system is going to schedule the executions of these different processes. Okay. Now, operating system schedule is scheduling is done mostly in the software level. Okay, in operating, it's a part of the operating system. It's called a scheduler. You're going to perform this job. There are two different levels of scheduling. Okay, one is called the long-term scheduling. The other part is called short-term scheduling. Okay, so the long-term scheduling decides when a process should enter the ready state. So once the process is created, so it's actually going to be loaded into the memory, and then the first thing the operating system needs to decide is, should I actually put this process into the ready queue? So waiting for the CPU to execute it. Okay, so this is actually done by the long-term scheduling. Okay, so when a process is created, remember that you have three basic states: the ready state, and then running state, and what's the other state? It's blocked, right? So the process basically running back and forth between these three different states. But when the process is first created, it should be normally in a new state. Okay. So the new state, it's a state, but it's normally not ready to be executed. So the long-term actually schedule need to decide whether we have enough resources for all the processes. So long-term actually scheduling can decide whether I should put the process into the ready state. So once it's in the ready state, then the process is going to be put in something called the ready queue. Which contains all the processes that are fighting, all the processes that are fighting for the CPU. Okay. Now, when I say fighting for CPU, that means everybody say, I'm ready, CPU, please actually pick me, so I can actually, do my job. So then who's going to actually decide which process is going to be loaded into the CPU? And that's the short-term scheduling. Okay. So, so the long-term scheduling is basically less frequent than the short-term scheduling. So it's basically actually going to be kicked in when a process is just created. And when the process is created, PCB is created, then the long-term scheduling can decide whether I can actually put you into the ready queue so you can fight for the CPU. Okay. So long-term scheduling decides which processes are moved to the ready list to compete for CPU. Okay. Also, when the process is suspended, okay, for whatever reason, so the operating system decide not to, run these particular processes. You're suspended. So in that case, whether we can actually bring you back or not, then it's a decision that the long-term scheduler is going to do. Okay. So long-term scheduling is a kind of a scheduling part that decide whether I'm going to bring a process in to compete for the CPU or not. So it's less frequently used. Now, most of the scheduling algorithms we are discussing now are basically focusing on the short-term scheduling. And short-term scheduling decides which of the ready processes should run next on the CPU. Okay. So that's the reason why short-term scheduling moves processes between the ready list and the CPU. Okay. Now, if there's one CPU, then pretty much majority of the process is going to be in the ready list, and only one process is in the CPU, one lucky one. Okay. Now, when this lucky one was actually complete the job, and then the short-term scheduling algorithm are going to pick the next process in the ready list, and then load the process into the CPU. So the short-term scheduling algorithm always pick who's going to be the next to use the CPU. Okay. Also, the short-term actually scheduling also decide when a currently running process becomes blocked. For example, currently the process is actually in the CPU and it's running. And then one of the actually instructions says, okay, I cannot continue unless you provide me more inputs. Then the process is blocked. And then later, when the data is available and when everything's ready, then in that case, the short-term actual schedule is going to put the process back into the ready line, okay, into the ready line, ready list, okay, and then fight for the next CPU turn. So that's the other task that the short-term schedule is going to do. Now, scheduling has two different types. One scheduling is called a non-preemptive scheduling. The other one is preemptive. Okay. So non-preemptive schedule algorithm allows the running process to continue until process terminates or blocks on a resource. Okay. So non-preemptive basically means whenever the process takes the CPU, then the process is going to continue to use the CPU unless the process voluntarily terminate itself or voluntarily block itself. And then the scheduler, short-term scheduler says, okay, so the current process is not using the CPU anymore. Then I'm going to pick the next one. Okay, so that's non-preemptive. This is basically, it's on a voluntary basis. Now the preemptive scheduling, so in that case, the scheduler really has a key. The scheduler can decide whether I can remove the current process off the CPU and allocate a next process into the CPU. So in that case, preemptive basically means I have a power. The scheduler has a power to change the processes from CPU to ready list, okay, or move the process from ready list into the CPU, okay. So preemptive actually scheduling is more powerful, but it has some kind of cost because the scheduler is going to frequently move the process back and forth between the CPU and the ready list. So this is going to take some time. This is going to actually have some kind of cost. Okay. Now, normally, the preemptive scheduling are normally going to make the decision whether I'm going to switch the process from the CPU to which the process in the CPU, which the process in the ready list. It's basically based on a couple of different conditions. So the decision is made whenever a new process enters the ready list. Okay. For whatever the reason, this new process is more important than the process which is currently in the CPU. So then the scheduler decide that I'm going to actually take you away from the CPU and I'm going to actually load the new process. So this new process is more important. Okay. This is actually one, the decision going to be made. This is one case. Okay. Now the other case is that a previously blocked or suspended process re-enter the ready list. Now this case is almost the same as the first case. If you think about the blocked or suspended process as, if you interpret this as just like a new process, then it's basically the same as the first case. So there's a new process, just new process just entered the ready list. Okay. Now the third case, which is actually more popular and widely used in modern computer system, is that the operating system periodically interrupts the current running process to give other process a chance to run. In that case, so if you have multiple processes, fight for the CPU. Now, with non-preemptive, once process one takes the CPU, process one can actually take the CPU forever. If process one decide to, stay in PC, never, or for whatever reason, process one is trapped or running into some kind of infinite loop, then everybody gonna suffer because process one never gonna actually quit. So that's a problem, So it's kind of like based on voluntary basis. So if process one takes the CPU, then everyone just rely on the process one. If this guy is nice, then say, oh, I have enough of CPU, so I'm gonna actually, I'm gonna, so I'm gonna quit and then let the other people to run. But it's now the preemptive case, like a particular third case. It's basically based on the design, operating system design. If the scheduler actually have some kind of a preemptive scheme that it will allow all the processes have chance to run. So in that case, the operating system can actually, allocate a certain time, saying, okay, I'm going to allocate the CPU into a small block. Okay, so for each block, like every second. So then I load the process one into the CPU and then run for a second. And then I'm going to take the process one away, load the process two. And I gave a process two the same amount of time, just 1 second. And then once the process two actually complete 1 second, then I'm going to take process two away and allocate process three. So basically, the scheduler going to actually take the turn for each of the processes. So in this case, the operating system can periodically interrupt the current process running program processing. Okay, the interrupt basically happens every second if the time period is 1 second. Okay, now this scheduling algorithm is a very well-known scheduling algorithm called round robin. It's called a round robin. So that's something we're going to talk about a little bit later. Okay. So how the scheduler going to allocate the processes? Okay. So mostly it's based on the priority of a process. So typically in any actually system, a process has a priority. The priority is just a number, okay, a numeric value that which basically indicates how important this particular process is. Okay, so if I just say, okay, I set the priority from 0 to 10, okay? 0 means highest priority, 1 means second highest priority, and the 10 means the lowest priority. So once I actually allocate the process, each process is going to have a priority number, a numeric value that indicate how important the process is going to be. Okay, then the scheduler basically going to pick the next process based on the priority of the process. This is typically the case. Okay. Now, so the priority could be a constant value assigned when the process is created. Okay. Or the priority could be a dynamic based number. So the priority of a process can change. So the process may enter the ready list initially as a low priority process. And then the priority of the process may increase. So that number is flexible. It can actually move back and forth. It can change. That's basically the dynamic based priority. Now, some of the priority is constant. For example, if in the operating system, in the computer system, you may have many different processes, and some of the processes is definitely more important than the other processes. Okay, for example, if you're running a computer system, so some of the processes are basically running to do the security checking. Okay, just monitor the system, make sure that there's no virus going to attack the computer system. If the viruses come in, then these processes can actually kick in and just fight with the virus. So, like some of the antivirus software. Okay, and these antiviral actual process going to be running on the background. They are always running. Okay, they should have high priority, right? Now, the other process is like your user process. For example, you start to play the computer game. Okay, so it's fine. If your computer is actually, the CPU is free, then you can actually play the game. But whenever some more important process is actually in and want to use the CPU, and the game program should give away, to a more important processes. So this is basically done by the scheduler. Okay, now it's based on the priority. Okay. Now, so you may have actually kind of scenario. So you have a process 1, process 2, process 3, process 4, process 5, process 6, process 7, process 8. They are all waiting in the ready list, or sometimes mostly I call the ready queue. Okay. So process 1 is at the beginning. Process 2 is next. 3, 4, 5. Okay. Now, when the current CPU is available, the scheduler gonna pick which one should be selected. And then the scheduler say who is next. Okay, there are 8 processes in the ready list, and then the process The one has a priority 2, process 3 has 4, 0, 5, 0, 1, 8, 9. Okay, assume that the 0 has the highest priority, and that's lower. Now, who's going to be the next one? Now, then scheduler actually find out there are 2 processes with priority 0, or priority, actually highest priority, P3 and P5. And then in this case, the arbitration rule decides which process should proceed if two or more processes have the same priority. So one approach is that they randomly pick a process like a process 3. Okay, you go and run. And once the process 3 finishes the job, and then it will be put back in the ready list. And then if the next one is process 5, and the process 5 will be picked. Okay. So this, the arbitration actually going to decide. Sometimes it's also based on the first come, first serve. Sometimes it's just to actually randomly pick among all the processes with the same priority. Okay. So now we need to actually figure out, okay, who actually going to be the next one. So we know that it's based on the priority. Okay. So now how can you decide which one should have high priority, which one should have a low priority? Okay. So these are the common parameters used to compute shorter-term priority. Okay. So these priority include like arrival time, and also the departure time, the point of the time when the process leaves the ready list by entering the blocked or suspended state, and arrival time basically the point in time when the process entered the ready list. Okay. Now also the attend CPU time, the amount of CPU time used by the process since arrival. Okay. So real time in the system, the amount of actual time the process has spent in the system since the arrival. Okay. Also the total CPU time, external priority. Total CPU time basically means the amount of CPU time that the process will consume between arrival and the departure. So this basically tell how long the process is going to actually use the CPU. So what's the boost time, so for the short-term scheduling, the total CPU time is the same time as called a CPU burst. Okay, so if I have 2 processes fighting, or 3 processes or 4 processes fighting for the CPU, who's going to be next to grab the CPU? And then the CPU burst, total CPU time basically just measures, okay, I have 4 processes, process 1, 2, 3, 4. And process 1 says, okay, once I got the CPU, I only need the CPU for like 1 second. And the process 2 say, oh, I need 2 seconds. And process 3 says, I need 10 seconds. And process 4 says, I just need 5 seconds. Now, who will get the CPU? Well, it depends on various different factors. If the scheduler say, okay, process 1 only need 1 second of CPU time, so I'm going to allocate the process 1, because once the process 1 grab the CPU, this process will only just stay in the CPU for 1 second, because it will, after a second, it will actually quit, because it just need a 1 second CPU burst. And the process 2, actually 3 has 10 seconds. Okay, so once the process 3 is actually grabs the CPU, then it will stay in the CPU for at least 10 seconds. Okay, that's one of the very important criteria to decide who's going to be the next one. Now, external priority is based on the other facts. For example, if you have two processes, one process is created by someone who pay more money than the other process, and that's external priority. So it looks like most people just say, "Oh, this guy paid more money to run the process, so I should give that process high priority." Okay. And also the deadline and the period. So each has its own definition. Deadline basically means a point in time by which the work of the process must be completed. Okay. If the process has a very tight deadline, like most of the real-time system, then this process definitely should get given a high priority. Okay. Many times these kind of process are called a real-time process. Okay. Now, real-time process is actually very important. Real-time, in some of the systems are called a real-time system. So many times, the real-time system that which contains a lot of real-time process, that these process has to be executed within certain period of time. Okay. Otherwise, you're gonna cause some trouble. For example, like the computer system in the automobile, in a vehicle. Okay. So now people are talking about all these autopilot, system. So the autopilot system gonna use a lot of sensors to sense the environment. Also use the radar to detect any objects. Okay. So if the sensor or the radar detected that there's an object before the vehicle, in the middle of the road, so then the autopilot system gonna kick in and they're just saying, okay, we have to actually apply the brake, to stop the vehicle. So this process is definitely has a deadline, right? So if a vehicle is driving at like 60 miles per second, no, per hour, 60 miles per hour, and it just detect an object just a couple of hundred feet away. So the vehicle is actually driving at the very fast speed, and then you have to stop the vehicle within certain time period. In this case, this process should have the highest priority. So now your system on the vehicle is running other applications like playing the music and doing some other processes like climate controls, then they should give away to that particular process. Okay. So these are all the different criteria when people use to apply for the for what kind of priority you should actually assign to a particular process. Now, also, the priority of the process is also depend on these different criteria, the different parameters, and also depend on the purpose of the system. Okay. So for some system, one parameter, this particular parameter is very important. And for other system, the other parameters are more important. As I say, for the real-time system, the deadline is the single most important factor. Okay. Now, some other criteria is like in a general computer system, the criteria could be the CPU utilization, right? So if you actually running a computer system, you want to have a high CPU utilization. So that means your CPU can be always busy. So you can have very effective use of your computer system. Now, so the scheduler should actually allocate the CPU processes in a way that your CPU utilization is maximized. If that's the priority, then your system scheduler is going to be definitely different from the scheduler that they're running on the real-time system. Because when real-time system, the timing is so important, and the son of the process has to be completed no matter what happens. Okay, so there are very different parameters, and also the priorities depend on what is your actual goal for the system. Okay, so the priority for the long-term scheduling, which decides when a new process should enter the ready list, also use the concept of priority. And the long-term priority can be based on the same parameters as the short-term priority. So there should be no difference between long-term, in terms of priority, long-term priority and short-term priority should be the same. Okay. But you really need to realize that the long-term priority is less frequent than the short-term priority. Long-term scheduling is less frequent than the short-term scheduling. Okay, and so the decisions are typically made at a higher granularity of the time, So that means the arrival time and departure time. Okay, when the arrival time, it means that you should actually change the state of a newly created process from new to ready. Okay, a departure time, when you actually, change the currently process, which complete the job to terminate the state. Okay. So that's why the attended CPU time and the total CPU time basically have the same different meanings for short term and long term. That's something we can see in the next couple of slides. And when we actually talk about the various different scheduling algorithm, so the attended CPU time and the total CPU time has different meaning for long term and for short term. Now the scheduling is, you have to actually discuss the scheduling for a different kind of processes. Okay. Now the first actually thing we're going to talk about is scheduling for batch processes. Okay. So the batch processes just typically are running in some of the huge computer, mainframe computer system. So you actually have a couple of tasks. You want to run a couple of tasks. And these processes are actually wait on a line to fight for the CPU. And once the process is selected, then it will be actually take the CPU and run. And then the next one. So basically it perform a long running and generally repetitive task that does not require any intervention from the users. So in 1960s and 1970s, when the mainframe computer was the most popular, computer systems, and they are very expensive. These computers are very expensive. There was no PC at the time, no personal computer, so no micro actually computer. So all the main computer systems are managed and maintained by either a corporation or computer center. So the CPU time is very precious. So if you have any job, any tasks, so if you're actually running a project, so then you need to actually schedule time in the computer center to run your program. Okay, so normally, so you can log into the computer system on the designated time. So So normally you're going to schedule time, and the guys in the computer center are going to say, okay, so you're going to be able to log into the system and run your program from 1 p.m. to 5 p.m. I gave you 4 hours windows. So if you have multiple users try to actually fight for the computer resources, it's just, you just basically wait in a line. And if you have people before you, then you have to wait for the person before you to complete his or her job, then it's your turn. So that's basically the batch system. Okay. So each of the processes are called batch processes. Now, you can interpret the batch scheduling just like, say, you have a couple of tasks. 1, 2, 3, 4, 6. And when new task is coming from here. And here, you're going to pick who's going to be the next process to run. Okay, it's actually wait in the line. And here's the CPU, the computer system. Now, the simplest scheduling algorithm people find out is called FIFO. Okay, so first in, first out. Okay, it's just like you're waiting. You want to buy a lunch in McDonald's. So then you go to the McDonald's and then you find out a couple of people already before you. So you just wait on the back. Okay, wait for other people to complete their purchase. So that's the FIFO. Okay. FIFO is also called first come, first serve. So it's a FCFS. And schedules process strictly according to the process arrival time. So who arrives first will get the CPU first. Okay. Now for the FIFO, if there are a couple of processes arrive at the same time, exactly the same time, then the arbitration rule going to apply. So you're going to randomly pick a one to actually take the CPU. Okay. So FIFO is very simple algorithm. And also, typically FIFO is no preemptive. So that means if the process is currently in the CPU, unless the process actually finished the job or quit, then other process have to wait. Okay. So FIFO is non-preemptive. Now this is an example. Okay. So I have 3 processes. Okay. And these are the arrival time for each of the process. Process 1 arrive at the time 0. Process 2 arrive at the time 1. Process 3 arrive at the time 3. And the total CPU time for each of the process actually is 6, 3, and 2. So if we draw this chart, sometimes we can call this Gantt chart. Okay, so if we draw the chart, then we're going to say process 0 arrive at the time 0, right? Arrive at the time 0. So process 0 get the CPU, and they will execute 6 time unit from 0 to 6. And complete the job. Okay. Now process 2 arrived at the time 1. So even though process 2 arrived at time 1, process 2 cannot get the CPU because process 1 is currently using the CPU. So process 2 has to wait. And the process 3 has to wait. Okay. Now, when process 2, when process 1 finished the job, and then the scheduler going to pick the next process based on the first come, first served rule. So that means process 2 going to get the CPU because process 2 arrived before process 3. So process 3 start to run after process 2 actually complete the job. So this is basically the order of executions. So FIFO is so simple. It's pretty simple. There's no questions, right? Now, let's take a look at the same problem. Not exactly the same problem, but similar problem. But I'm going to slightly change the order of arrival time. Okay. So I still have the same 3 processes, P1, P2, P3, and each process has a total CPU time 632. And then, so these are the same, but I slightly change the arrival time. I'm going to make the process 3 arrive first, and process 2 arrive second at the time 1, and the process 1 arrive at the time 3. So now process 3 arrive first. So when I draw the Gantt chart, then the process 3 going to actually get the CPU first, right? And execute for 2 time unit. Once the process 3 is done, now who's going to be the next one?
Process 2.
Process 2. They're going to execute 3. 1, 2, 3. And then the process 1. 1, 2, 3, 4, 5, 6. Okay. So now, if you look at the total, actually, CPU time for all 3 processes, they're going to actually complete at the time 11, right? And here, they also all complete at the time 11. Now, you're probably going to ask, well, it looks like the total CPU time is still 11. What's the difference? Okay. Now, let me actually think about this. Okay. Suppose this is actually a supermarket. You have 3 people try to check out, and one person just grab a can of drinks. Okay, so he just bring a drink, just very simple. And the next person, he or she just take a couple of items. Okay, and the last person, he or she just have a very, very big cart, shopping cart, with tons of stuff in the shopping cart. Okay, now you can actually think about the guys with just a can of beer or a drink is the process with the actually fills the total CPU time, and the next guy has the second actually number of CPU time. The guy with a big shopping cart has actually longest actually total CPU time, right? So now, what are you going to feel? So if you actually, typically, you should actually let the guy with, just one with the drink gonna actually check out first, because he or she probably just take a couple of seconds. He or she just pay the cash and get the exchange and take the drink out. It's very quickly, just very quick, just a couple of seconds. And the second guy probably going to take like 10 seconds or 15 seconds, half a minute, okay? Because he or she has a couple of items. And the last guy with a big shopping cart are going to take like 5 minutes to complete the checking out. Okay, so What is a feeling? Because if you let the guy with the drink check out first, he will be very quickly leave the supermarket, and then next one. And then the last one with a big shopping cart, they're gonna stay there for 5 minutes and checking each of the items out. Now, the other scenario is that if this first guy with a big shopping cart arrive first, and he or she start to check out, and the other people just wait behind this guy and wait like at least 5 minutes, you know. So you think which scenario is better, right? So we're gonna come back and talk about this again. Now, the second scheduling algorithm is called SJF. It's called shortest job first. Okay, so the shortest job first algorithm, also known as shortest job next, you know, schedules process according to the total CPU time requirement. If we have 3 processes, okay, they arrive at approximately the same time, then we hope that the process with the shortest total CPU time check out first, and then the next one, then the next one, right? So the shorter the required CPU time, the higher the priority. So if multi-processors have the same CPU time requirements, then again, arbitration rule can select. Okay, and also the shortest job first is also non-preemptive, but there's a difference between shortest job first and the FIFO. Let's take a look at another example. We're talking about the same scheme, P1, P2, P3, and total CPU time 632, and arrival time 013. Okay, so when process 1 arrives, okay, so when process 1 arrives, process 1 is the only process that requested for CPU, right? So the process 1 will get the CPU and start to execute. Process 2 arrives. Process 2 cannot do anything because this process 1 is in the CPU. Remember, this is non-preemptive. Okay, so non-preemptive means you cannot kick anyone out of the CPU. However, when process 1 finishes, and then both process 2 and process 3 are in the ready list. Now, if we use a FIFO, we're going to check who's going to be next. Then P2 actually arrive first. So based on the FIFO, P2 will get the CPU first. Okay, and the P3 second. Next. Okay, but now we use shortest job first, and then the operating system going to check. Okay, who has the shortest CPU burst time? Okay. I don't care who arrives first, because all I see is I have 2 actually processes in the list. Who has a short CPU burst? And the P3 says, me. Okay, I only need 2 CPU time. And the process 2 need 3 CPU time. So process 3 get the CPU next, because process 3 has a shorter CPU burst. And then process 2. You see the difference between these 2, right? Yeah. So here it's based on the order. Here, you can actually see there's difference. Now, either case, the total actual CPU time is still 11 for all 3 processes. It doesn't really matter, okay? So you don't actually save any CPU time. It's just a different order of execution. So that's shortest job first scheduling. And we will come back and discuss the performance for each scheduling algorithm, okay? And then we're going to discuss another scheduling algorithm called STR. It's called the shortest remaining time algorithm. Shortest remaining time algorithm schedules the process according to the remaining CPU time needed to complete the work. Okay. Now, what's the difference? Let's take a look. We still have these exactly the same situation. Okay. Now, when process 1 arrives, no other process is actually in the CPU. The process 1 is the only process in the ready list. So process 1 will get the CPU. And then when process 1 runs for 1 time unit at the time 1, so process 2 arrives. Okay. Now the scheduler, the operating system scheduler at this moment gonna figure out, okay, I have a process 1, process 2, process 3. So when at the time 0, process 1 arrives, right? So process 1 get the CPU. Okay. And at the time 1, process 2 arrives. Okay. So then the scheduler gonna figure out what is the remaining time for each of the process. Okay. Process 1, the total CPU time is 6, but process 1 has executed for 1 actual time unit. So the process 5 has 5 remaining time, right? 6 minus 1, because it's just executed 1, so it has a remaining time. Now process 2 arrives, it has 3 total CPU time. So I'm gonna, let's see. Let's do this. I'm gonna let me erase this. So I just put the remaining time. So the process 1 arrived at time 0, the total remaining time is 6. So process 2 is not there, 3 is not there. Now when at the time 1, process 2 arrives, the process 2 has 3 total CPU time. And process 3 is still not available. So now the scheduler can actually figure out who's going to be the next one. So who has the shortest remaining time? Process 2, right? So the process 2 going to grab the CPU. Okay. And the process 2 start to run. And when process 2 execute at the time 3, because every time when a new process is joining the ready queue, the scheduler going to stop and check. Okay. At this moment, so process 3 arrives. Now, how much total CPU time for process 3? It's 2, right? Now, what's the remaining time for process 2?
One.
Yeah. Only 1, right? Because when process 2 joined the ready list, and it has a 3, but it from 1 to 3, it just executed for two time units. So there's only 1 remaining. What about process 1? Still 5, right? Process 1 is unlucky one. So the process 1 still actually has 5 left remaining. So then the scheduler going to pick among these 3. So 5, 2, 1. So process 2 is the shortest one. So the process 2 going to continue. That's the reason why process 2 continue. Then when process 2 complete the job at time 4, so process 2 is done. And then process 1 has a 5 time units. Process 3 has 2 time units. And then you pick process 2, right? Run at time 6. Okay. So at the time 6, process 3 finished the job. Process 2 is not available anymore, and the process 1 has a 5. Now, process 1 is the only one in the ready list. So process 1 complete the job at the time 11. Okay. So every time when a new process join the ready list, or any process leave the CPU, then the scheduler gonna actually decide who has the shortest remaining time. Okay, and continue to run this one. Any new process join the ready list, or existing process actually leave the CPU, then you have to, make a selection. That's the SRT, the shortest remaining time. Again, the total CPU time is still 11. Okay, but actually I'm lying. The actual total CPU time is not 11, because remember, every time when you have context switching from process 1 to process 2, you're gonna take some time. It's a context switching time, right? Because you have to save the information of the current process 1, into the process control block, because when process 1 is resumed, then you have to reload the data from the process control block. So you need to save the data into the process control block, and then you need to reload the data or load the data from another process control block. So here you have sometimes context switching time. So you're gonna have 3 context switching time. Now, context switching time is not free. It's not 0, okay? But sometimes we choose to ignore them because we just assume that the let's say context switch time is 0, but it's actually not 0, because it's gonna take some action. So if you have a very frequent context switching time, if these context switching time accumulate, you're going to add up some kind of CPU time, and these CPU times are wasted. They don't do any meaningful job. Okay, they just actually load, save the work to a PCB and load the work from the PCB. So it's basically does not do any meaningful job. So even though we say all these 3 cases, FIFO and the shortest job first and the SRT, they actually eventually the total actual CPU time are the same, but they are not always the same, because it depends on how frequently they actually do the context switching. But they are the same if we actually assume that the context switch time is 0. Okay. Any questions on this? So these are 3 different algorithms. And now the next one, that's the important one. And we're going to talk about the performance of the algorithm. Which one is better? Which one is the best? Okay. So we can actually measure the performance using a couple of criteria. One is called the turnaround time. So a process turnaround time for a process is the turnaround time of a process is the time between arrival and departure, and is the sum of the total CPU time and the waiting time. Okay, that's the turnaround time. Let's go back and check what's the turnaround time for each. Okay, turnaround time measures the time when process arrive and the process departure. Okay, so let's say what's the turnaround time for P1?
6.
6. It's a 6 minus 0, right? That's departure time. That's arrival time. And now what's the turnaround time for P1? So the departure time is 9 because the P1 finished the job at the time 9. What's the arrival time? 1, right? This is the arrival time. $11. That's a departure time. What's the arrival time?
3.
So it's also 8, right? So that's turnaround time for each individual process. And the average turnaround time is calculated like, you just add them together, divided by 3. So that's, what is that? 16% 22 divided by 3. So that's
7.33333.
Okay.
Yeah, 7.3 repeating.
Okay. So that's the average turnaround time. Okay. So that's called ATT. Now let's take a look at this case. Okay. If we switch the time, so what's the turnaround time for P1? 11 minus 0, right? That's longer.
Well, it arrives at time 3, so
time
it would
3.
be 8.
3. It will be 8. Okay. Let's just finish this one. This is actually finish times 5. Arrival time is 1, right? That's complete time is 2. Arrival time is 2, right? No, arrival time is 0. So that's 2. Is that right? So the turnaround time, average turnaround time is 8 plus 4 plus 2 divided by 3. So that's
14.6 repeating.
Okay. So definitely this is better than the previous case, right? So that's why, the average people feel better on this case because the shorter one finished job first. Okay. Now you can actually just calculate the turnaround time for in each case. Okay. So now for the turnaround time for this one, P1 is here and finish at so P1 is 11. P2 is finish at the 4. Arrive at 1, so it's 4 minus 1. And P3 is finish at 6, arrive at 3. So that's 11 plus 3 plus 3 divided by 3. Okay. So it sounds like in every case, it's always better than FIFO, right? FIFO is probably the worst. It's actually, so you can actually see this, diagram over here to see what's the differences. The FIFO is the worst. It's a 7. And then the shortest job first is a little bit improvement, but the problem is that even though it's a shortest job first, because P1, which is the longest one, still actually arrive first and still take the CPU a very long time. So that's why it's still big, not big improvement. But this is actually a good one. Okay. Okay, I think that's pretty much all for today. So we're pretty much running out of time. So I'm going to actually start to, post some of the work for you. You can start to work on the problems, exercise problems in chapter 3, but since we haven't finished the chapter 3 yet, so you can I can actually put a very late due date, but you can start to work on this. So if you have any question, just ask. And also, I just want to emphasize this. If you actually haven't done the exercises, the assignments for the previous modules, chapters, please let me know, because this is always my philosophy. Actually also it's stated in my syllabus. So I always accept a later submission, but you will get some penalty. Otherwise, you still get some points, still get some credit for your work. So if you actually haven't submitted any of the previous assignments, let me know. I can actually, just, allows you to complete it with some, penalty. The penalty is not really that big. If you can check the syllabus. I have specified this in the syllabus. Okay, so I think that's pretty much all for today. And I think after I complete the chapter 3 and 4, maybe we can schedule a test. Maybe just after I've finished the chapter 3. Because for this semester, we actually lost many days. Yesterday, last Tuesday was was a wellness day, and also we have a snow day, so we just missed some classes. So we have a kind of delay in our schedule, but I think we can manage to make it up. So okay, that's pretty much all for today. So
see you on Tuesday, Professor.
See you on Thursday. Oh, see you on Tuesday. I'm sorry.
Tuesday.
Next week. Okay, so enjoy the rest of the day.